All right, so for 14.2, we were talking about double integrals. Let's do okay. I can't read what I wrote here. Let's try to do this though. So find the volume of the solid below Z equals 2x plus 3y and above this region. I'm just going to draw the region here. So let's go with this. Oh, it's y equals x, as I said. Okay, so you have, let's not worry about the exact picture here. This guy is a plane though, right? Z equals 2x plus 3y, and I don't think I won't draw the whole thing, but it's, right, you got a plane moving up there according to, right, z equals 3y, and then z equals 2x, and so you're going to get a plane that just comes up like this out of the board, right? As x and y grow, it's going to be positive. So all we really care about is that it's up above here, right? If you think of this as your x, y, and the z coming out of the board, your surface is above there. And so this makes sense to talk about the solid that lies below this and above this region, okay? And so this is, I guess, one application of the double integral is that the volume, right, is the double integral of the solid up, or the surface up above, and then you just set the bounds to be determined by this region, right? So if you call this region R, the volume is the double integral over R of your function 2x plus 3y dA, right? And so we just have to set up the appropriate double integral. So how would we do that? What would be the bounds? What would be the order of integration that makes the most sense? Do we want to do dy and then dx, or dx and then dy? Any thoughts on that?
dy here.
Okay, why dy then dx?
Or the opposite, because we have the x.
We need to
So let's look at this. If we're going to do dy then dx, we go from, x would go from 0 till, where's this?
X over 2.
So when x over 2 equals 2, right? So that's 4. That make sense? So if we're going to do the dx on the outside, so don't write this down yet, because this is not the way to do it. But let's see why that's the case. So if we wanted to say, go about it this way, right? You'd have to go x from 0 to 4, and then where would your y's go from?
from x to x over
0 to x over 2.
No, we're talking about this region up here, right? So for an x, you go from here to there. So you go from x over 2 to x, but then what if I picked an x over here? I'd go from x over 2 to 2, right? And so you change which function is your top function when you look at it this way. Now you could do that. You could break that up into two integrals and do, right, do the integral from 0 till 2, you know, and then x over 2 to x, plus then the integral from 2 to 4. That would be fine. It wouldn't be much of a difference. But I'd say it's better to just turn your head and look at this in the other direction. Okay, so now what are the bounds for y? 0 to 2. And now there's just one, right, so I'll erase these guys. Now for a fixed y, we clearly have a bottom and a top for that whole range, right? It's the same top and bottom. So you're going to integrate from this function to this function, and just be careful, what are the functions? X equals y, right? When you turn your head, you solve for x to get your function. So this is y, and this one is x equals 2y. So you're going to integrate from y to 2y. Does that make sense? So let's finish this off. 0 to 2. What do we get when we integrate with respect to x here?
X squared plus 3y.
Okay. So 0 to 2, x squared plus
3yx.
3yx. I'm going to write it xy for whatever reason. I like the x in front, but it doesn't matter. And then the 2y and y get plugged in, right? So that gives you,
Plus 3.
it'll give you 4y squared minus y squared, right? And so what do we end up with? 3y squared. And then this one will also give us
6x. No.
6y squared, right?
6y squared.
I guess here, let's just write it all out. I'm going to confuse myself. 2y squared minus y squared for that first one, right? And then this one is 3 times 2y minus 3y, right? So, again, if you want to do it in your head, go for it. But what do we end up with? We get 4 of them minus 1 of them, so 3, and then 6 minus 3, right? So we end up with 6 total. Does that make sense? So 6y squared dy, and then what? 2y cubed, 0 and 2. Okay? All right. Yeah. All right. Any questions so far? Okay. So, last thing for this section, and I'm going to not spend a ton of time on this because we'll cover more of it when we get to triple integrals. Okay, but if we want to be able to calculate center of mass, and so the idea is you have some object in the xy plane, right? And you have some, so we'll say a lot of times a plate. So you have a plate here, and the density of the plate will vary as you move around on the plate, right? And so if you think about how would you, right, find the mass of a plate if you knew the density, well, you could break it up into a bunch of little pieces and approximate the density, right? And then you add those up, you take the limit, and the same thing happens every time. You get this integral that comes out. And so if this plate has density rho of xy, so now it's a function of xy, right? The density changes as you move around the plate. The mass, so I'm just going to write down our formula. The mass, which we'll call little m, is just a double integral, let's call this region R again, over the region of your density function. Okay. All right. And then let's just say moments. M sub x. Okay, so the moment m sub x is the moment is measuring sort of the tendency to rotate around the axis that's given. And so you can do this for other lines, but we'll just stick with the x-axis and the y-axis. And I don't know that I want to say much more maybe we'll say a little bit more when we get to the 3D case, but the idea is that, right, if you put a bunch of weight further away from the x-axis, that's going to have more of a rotational tendency around the x-axis, right? You've got extra weight pushed further out. Just think of, working a wrench or something, right? You have more force as you pull yourself out. And so that's why the tendency to rotate around the x-axis has this y in front of it, and then vice versa. And then the big thing is that your center of mass is just x bar, y bar. And so we just compute these by, well, right, your, I'll just write it up. So it's just your moments divided by m. Okay? And just pay attention that they're flipped over, right? So your m, or your x bar has the m sub y above it. Because again, you're trying to get the tendency to rotate around the y-axis. That's going to give you an x value, essentially, right? So you're going to measure that. So let's just do one example here. I don't like the one I wrote down. Let me grab a different one. So it says find the center of mass. And here we'll just do. Let's just do. This one happens to be 59, but it's a decent one. So it says find the center of mass for a plate occupying the region R, and so R is the right half of the interior of x squared plus y squared equals 4, and your density function rho is just x. Okay. So finding the center of mass just means compute all of this stuff, right? So you have to compute the mass. You're going to have to compute m sub x and so on. So first thing first, what's that? X squared plus y squared equals 4. It's a circle of radius 2, right? So you're talking about, oh, that's a sloppy looking region, but you're talking about this region here. And so when you start to compute things, right, your mass is just, oh my God. All right, I guess that's staying there. A couple of years ago down in 125, I was trying to pull the thing out and it completely broke out of the ceiling, fell on my head. It was very ugly. Anyway, I guess I'm not moving that today. So what mass, right, is just, it's a double integral over the region of your density function, which in this case is just x, right? And then you're computing double integrals, so you just use whatever method makes most sense. So when you're computing and your region happens to be a circle, what's your method? What's the best method to do? To convert to polar coordinates, right? Does that make sense? So you're going to convert this to polar coordinates, and then we should be able to get there. So when we do that conversion, what's the x become again?
R.
R cosine. And the dA?
R.
R dr d theta, good. And then in this case, what do our bounds go from?
Negative pi over 2 to pi over 2.
Okay. And from 0 to 2. Be careful here. Right. Some people will say, oh, that's 3 pi over 2 and there's pi over 2. And so I see a lot of times that people will integrate from 3 pi over 2 to pi over 2. You can't do that, right? It needs to be, you have to integrate along one counterclockwise arc, right? So if you could have started with 3 pi over 2, but then you have to go to what?
5.
Yeah, you'd have to go to 5 pi over 2, right? So just be careful. It doesn't matter. I think it's more, this makes the most sense, right? To think that's negative pi over 2 and then up to positive pi over 2. That doesn't matter. Okay, so now when you integrate that, well, let's just write it out. Negative pi over 2, pi over 2, 0 to 2. So we have r squared cosine of theta dr d theta. So what's going to happen when we integrate here? R cubed over 3, right? So we get what, 8/3? Cosine of theta, so we end up with 8/3 sine of theta negative pi over 2 to pi over 2. So what do we get there? Sine of pi over 2 is 1. Sine of negative pi over 2 is negative 1. So you'll get 8/3 minus negative 8/3, right? So you'll end up with 2 of those. So 16/3. Okay, so there's the mass. I guess we're after center of mass. Oh, I didn't say what we were after, did I? Find the center of mass. I think it was in the description. Okay. So, take a second, try to compute these two guys now, the m sub x and the m sub y with that in mind. So let's just slightly start this. So m sub x will be the double integral of what? Y(x), right? Yeah, and whatever method you use to integrate, you're probably going to use the same one because you picked that method because of the region, not because of your function, right? So even though you tweak this function, your region is still, it makes much more sense to do polar coordinates. So, all right, what do we get on the inside then? R sine, R cosine. Right? So it'll be a little trickier, but try that one. You'll end up with r cubed and then sine times cosine, so you'll have to do some bits of substitution there. And then on the next one, you're going to get a cosine squared. Remember, we know how to integrate that, so I try to remember that. Alright, so if we had a chance to get somewhere, I'm going to go through this one a little quicker than the last one. So we end up with r cubed, sine of theta, cosine of theta, dr, d theta. So when you integrate the r, what do you get? R to the 4th over 4, and then you plug 2 and 0 in. So 2 to the 4th is 16 over 4 is 4, right? So you're just going to end up with 4 sine of theta, cosine of theta. Is that okay? All right. So what happens after that? How do you integrate?
Can I make it into sine 2 theta?
Oh, I suppose you could do that. Yeah, that'd be one way to do it. Here, maybe I'll just give you two we'll do it that way. You could also have done u equals sine, right, or u equals cosine. Either one of those would work. You do it, but your way works well too. So remember, you have an identity that 2 sine cosine is sine of 2 theta. Does that make sense? And so you could split this guy up like that. And what do we end up with here?
2 sine,
2 sine of 2 theta, good.
2 sine.
Okay, so now when you go to integrate that, what do you get?
Negative cosine 2 theta.
Negative cosine of 2 theta, is that okay? So you'll get negative cosine, but 2 negative cosine, you divide by the 2. And then we plug in our bounds. So what do we have there?
0.
Plug in,
Yep. All plug in 0. Negative, negative 1.
okay?
Minus negative. There's another minus and then negative 1.
Okay. That's okay. I think we end up with 0 there. Alright, so I would say let's wait until we do the center of mass. But anytime you come up with 0, you should think, does that make sense, and go back and figure it out. But we'll come back to that in a minute. Okay. And so then we need what? M sub y still, right? So, and so that one will be x, right? dA, and so you'll get, again, keep your same bounds. And then this will be what? X squared, so that's
R squared cosine.
r squared cosine squared, r, yeah, theta. So r cubed. Okay, so just like the last one, right, when you integrate that r, you get the same thing, so you should end up with 4, in this case, cosine squared. How do we integrate cosine squared? Where's my hand?
1 minus cosine.
1 something plus.
Cosine 2.
Two. If it was sine, it's sine squared, it's 1 minus the cosine, right? So we use that identity. So we can cancel these guys. Let me just do that, right? Leaving us with 2 there. And so now we go ahead and integrate, and I'll just do this. 2, what's the integral of 1? Theta. And then plus sine of 2 theta over 2, right? You can cancel that out if you want, but just do that. And then we're going to go from negative pi over 2 to pi over 2. Notice when we plug the pi over 2's in, we get sine of pi and sine of negative pi. They're both 0. So that's all gone. And then when we plug, so we're just going to end up with what? 2 pi over 2 minus negative pi over 2. Okay? So just
2 pi.
whole pi. Does that make sense? All right, now we're pretty much done. Let me leave this region up as long as we're here. I'm here. And so your center of mass is then x bar, y bar, which is m sub y over x, m sub x, over m. Over m, and so you just fill those in. Oh, I just erased our m. Well, you guys have it in front of you, so you can remind me. So m sub y was 2 pi. What was our m again? It's like 8/3 or something, 16/3? 16 over 3? Okay. And then what do we got here? 0 over 16 over 3, right? So it's just 0. But did we care? It's what, 3 pi over 8, I guess, then?
Yep.
3 pi over 8 and then 0. That makes sense. So like I said, 0, don't get too alarmed, but anytime you see 0, you should think, does that make sense? So when you look at this plate, does it make sense that the center of mass is at, or in the y direction is at 0? Yeah, right, that's symmetric over the x-axis, and so if you're guessing where the center of mass is, you're gonna guess it's somewhere around here, somewhere on that x-axis. Does that make sense? So, again, you don't have to worry about it, you don't have to think about it, but if for some reason you notice that ahead of time, I suppose you could probably get by without calculating the m sub x, but you better write out your argument as to why you know you don't have to do that. I would say in most cases it's easy, it's better just to compute them and confirm you get the zero you think you should get. But anyways, I'll stop there. So we'll come back to center of mass and mass in calc, or in a couple sections. All the ideas that we've dealt with here in this section on double integrals will show back up for triple integrals, which we'll get to in a few sections. Anyways, we'll stop there.